Hello and welcome to Mysteries of Science. My name's Dan and I'm the editor of Science and Nature, the monthly magazine from the team behind The Week Junior.
And I'm Michael, the junior editor. On this podcast, we take a look at our favourite mysteries of science. These are the strange phenomena and bizarre events that have left scientists scratching their heads and, despite their best efforts, remain well and truly unsolved.
Say, Michael, what's that sound?
What sound?
Don't you hear it? That's weird.
Oh yeah, that sound. Well, Dan, what if I told you that was the sound of a black hole?
A black hole? Now, I've heard about these and they sound pretty scary. But what are they exactly?
So black holes are small regions of space where a great amount of matter is packed in and their gravitational pull is so strong that nothing, not even light, can escape.
Blimey, sounds powerful. But Michael, I want to know more. I want to know what's inside a black hole. I want to know what would happen to somebody if they got sucked in. And are black holes really eating up the universe?
I think it's time we went on a journey into deep space to get some answers. But maybe we should get out of the way of this black hole first before we get sucked into it.
Yeah, too right. This is Mysteries of Science!
Hi, my name is Dr. Maggie Adair-Pocock, and I'm a space scientist and a science communicator.
Dr. Maggie presents the BBC's Sky at Night. Here's how she defines black holes.
So a black hole is one of the mysteries of astronomy. They are objects that where the gravity is so dense that not even light can escape. Now that makes it sound very interesting because if light can't escape from it, how can you see it? And the way we observe them is by looking at the gravitational effect on objects around the black hole. So there's a sort of a structure to a black hole. If you get too close, beyond what we call the event horizon, then the gravity is so powerful that everything gets sucked in. But if you're outside the event horizon, you can still feel the effect of the gravity of the black hole, but you won't actually get sucked in. So that's one of the ways we monitor them.
So this event horizon is like the barrier from which there's no escape.
Yeah, literally the point of no return. And the event horizon is a sort of a sphere outside the black hole. And yes, if you get close to the event horizon, you are okay. But if you pass the event horizon, then the gravitational force of the black hole is so strong, yes, you just can't escape.
Right, I think I've got it. Do not pass the event horizon. Very important rule for the universe, for star travelling around the universe. And I also asked at the start, how are these black holes formed? Let's hear from another expert.
I'm Emily. I'm a professor of astrophysics at University College London. I use some of the largest radio telescopes in the world to study galaxies, how they form, how they evolve, and how their black holes behave.
So Emily is an expert on black holes, and she says that they're formed from collapsed stars.
Ooh, collapsing stars. But how can a star collapse?
So you have to understand it how a star works. So a star produces some energy at its center that creates a lot of pressure. And then you have gravity that tries to hold the star together. And as long as the star is shining, the pressure and the gravity balance each other out. But when a star dies, it stops producing all that energy and gravity takes over and makes the star collapse onto itself. So it becomes smaller, smaller and smaller and denser and denser and denser. And in some cases, it gets to the point where all the mass gets concentrated in a tiny, tiny place of space. And that forms a black hole.
Wow. So I think we're doing pretty well already. We're ticking off these questions. We found out what black holes are. I've found out how they're formed as well. But I think this week, as we're recording the podcast, we had the news that there's been a new photograph of something called a supermassive black hole at the middle of our Milky Way galaxy. And I wanted to ask Maggie if she could explain what these supermassive black holes are.
Yes, yeah. With a supermassive black hole, you up the ante. Supermassive black holes are what we find at the heart of galaxies. And although we can understand how a standard black hole can be formed, supermassive black holes, we're not quite sure. So they sit at the heart of galaxies. It might be that many stars sort of collapse in to form a supermassive black hole, but they are, yes, on a much, much bigger scale.
So I asked Fabio Picucci, who's a black holes expert from Harvard University in the US, to tell us exactly how big a supermassive black hole is.
Supermassive black holes are black holes that are more massive than 1 million times the mass of the Sun. So these are really cosmic behemoths, and we have discovered quite a lot of them, both close by. There is a supermassive black hole of 4 million times the mass of the Sun at the center of our own galaxy, the Milky Way, but also we've discovered them very, very far away, up to billions and billions of light years away. So supermassive black holes can be found typically at the center of galaxies, and we believe that they contributed in a very significant way to the evolution of the galaxy itself. And the maximum mass of black holes that we've found so far are typically about 20-30 billion times the mass of the Sun. So these are really cosmic monsters that sit at the center of very massive galaxies.
Goodness me, 20 or 30 billion times the mass, or the weight of our star, the Sun. That is incredible. And how does that actually compare to a regular black hole?
The event horizon of a supermassive black hole can be tens of times the entire size of the solar system.
So your standard black holes, their event horizons are the size of cities, but supermassive black holes, their event horizons can be about 10 times the size of an entire solar system.
Yeah, they definitely live up to their names for sure. And there's one right at the centre of our galaxy.
Yeah, it's called Sagittarius A star. It's around 26,000 light years away from Earth. And believe it or not, Dan, we can see it.
I know! That's the one I was talking about earlier. Sagittarius A star is the supermassive black hole at the heart of our Milky Way galaxy. And this is the first time it's ever been photographed.
If you are a grown-up, head to eventhorizontelescope.org. You can see the picture for yourself. Or, of course, you could just open the latest issue of Science and Nature to see it in our That's Amazing section.
I mean, it's just blowing my mind. I have no idea how they did this. How do you take a picture of a black hole in space, right? There's no light coming from it.
Well, I think we should speak to somebody who was part of the team which took the photo, Zero Yunsi from the Event Horizon Telescope project.
I'm an astrophysicist, and I work at University College London. I work in a department called the Mullard Space Science Laboratory, and I work on a few things in astrophysics, but one of my core interests is actually black holes.
Ziri explained for us what the Event Horizon Telescope project was.
It's a network of radio telescopes. So it's a set of telescopes that are spread all around the world, and the Event Horizon Telescope connects all these telescopes together and coordinates them so that they're all pointing at a black hole at exactly the same time.
So it's thanks to this Event Horizon Telescope project that we were able to take this picture of a black hole. Now, we told you earlier how you could see it for yourself, and if you haven't already, you might want to get it up and take a look, because Ziri is going to take us through the photo and explain exactly what it is we're looking at.
What we're looking at in this picture isn't actually the black hole directly. It's actually a ring of matter that surrounds the black hole. And that's what this big orange, almost donut, if you will, that you're looking at is. It's actually very blurry because that's because the resolution of the telescopes is still not high enough to capture all of the really detailed features in the image. But what you're looking at is matter that's been pulled in slowly by the strong, powerful gravity of this black hole. And as the matter starts to fall inwards, it starts to swirl around the black hole, much like water swirls down a plug hole. And as it gets closer to the edge of the black hole, to its event horizon, it moves faster and faster. And it can actually travel a very good fraction of the speed of light, so incredibly fast. And as that matter is moving faster and faster towards the event horizon, it gets really hot because of friction, and all the particles in that matter are rubbing up against each other. And it produces a lot of light. And that light is actually radiation across the whole electromagnetic spectrum, and we're picking up the radio waves that are produced.
Wait a minute, hang on. Did Ziri just say radio waves? Like like radio stations? Why would we be picking up radio waves?
The reason why we're trying to tune into radio waves is for the same reason that you try to tune into radio waves when you listen to the radio, and why radio waves are used for communications on Earth and elsewhere. And it's because radio waves do a very good job of traveling through clouds and around mountains and around the curvature of the Earth. And they also do a good job of traveling 26,000 light years from the center of our galaxy to us through all the dust and gas and stars, because they're very long wavelength, and so they're not easily scattered, and so they're not attenuated in the same way, and so it's easier to record a signal. And so that's what we did, and we recorded the radio light, or the radio waves, from this black hole, from the plasma that's around that black hole, and that's why you see a ring. And then the dark feature in the center of the ring, that's what we call the black hole shadow, and the black hole itself lives in that dark region inside that dark shadow within the bright ring that you see in the image.
So we've looked at a black hole, but how would you like to listen to one?
Absolutely. Listen to a black hole? Yes, please.
So remember that black hole we heard at the very start of the podcast? Let's meet the team who recorded it.
So, hi, my name is Dr. Kimberly Arcand, and I am a visualization scientist for NASA's Chandra X-ray Observatory at the Center for Astrophysics, Harvard and Smithsonian.
So, Kimberly has been interested in science from an early age and wanted to be an astronaut when she was growing up, until a trip to a theme park changed her mind.
I can't remember a time where I wasn't interested in science. I actually remember being in kindergarten and wanting to be a doctor, and then after that wanting to be an astronaut. And I will say, with the astronaut desire, that one petered out, I think, after about a year, because my parents took me to an amusement park nearby, and I was petrified of everything. I could not even go on like the high-powered swings without panicking. And so it wasn't too long after that I realized, maybe I'm better off with my feet firmly planted on the ground.
I'm with Kimberly there. I'm absolutely terrified of roller coasters.
Oh dear, love a roller coaster myself, but perhaps Kim, she can explain to us what a visualization scientist is.
So I specialize in visualizing data from our universe, in the sense that most of the data from NASA's Chandra X-ray Observatory, or the Spitzer Space Telescope, or even others like the Hubble Space Telescope or the James Webb, those telescopes are often looking at different kinds of light than what human eyes can see, right? The visible light, or the optical light that most of us are used to. And so if we're looking at things in X-ray light, like Chandra looks at, or infrared light, like the James Webb looks at, we have to translate it, just like you might translate speaking in French to speaking in Mandarin, right? You're moving from one form to another. And so it's my job to take the information that we have in one format, in a format that we can't see, and translate it into a format that we can see.
So the black hole we heard at the very start of the podcast was from the Perseus Galaxy Cluster. Here it is again to remind you of what it sounds like.
The Perseus Galaxy Cluster is this really massive cluster of galaxies pretty far away from us. And there's this just large amount of hot gas around a very central object. It's a very supermassive black hole at the center of the Perseus Galaxy Cluster. And that black hole is sort of erupting or burping into the space around it, which creates these pressure waves, which are actually sound waves. And that kind of, propagates or ripples out through the cluster's hot gas. So by using spatial software, scientists could actually take that data and translate it into a note that it makes. And that note is about 57 octaves below middle C. So that's really, really, really deep. It's such a deep sound that human hearing can't detect it. So what my partners and I did, Matt Russo and Andrew Santaguida at System Sound, what we did is we used more coding, essentially, to be able to take that note and translate it into a sound that you can hear, so back up into the range of human hearing.
This is brilliant. It's so clever. I love it. Just sort of mashing together music and science.
Exactly. And as well as Kimberly, we also spoke to Matt Russo, who she mentioned there. He's a musician and astrophysicist who helped create these black hole sounds.
Matt, we got everyone on this podcast.
For the past 5 years, I've been converting data from space into sound and music with my project System Sounds. And over the years, that developed into a series of collaborations with NASA. And so we have one running collaboration with the Chandra X-ray Center where we focus on image sonification. So we take images of astronomical systems like galaxies or clusters of stars, and we convert the image information into sound. So as part of that project, one of the systems we were going to look at was Perseus, the Perseus galaxy cluster, and we realized instead of just converting the shape of the image into sound, we can actually extract the sound waves from this image. So this was a very unique technique, and it's the first time we've been able to do that.
And the Perseus Galaxy Cluster is not the only black hole sonification project that they've worked on.
Oh, that sounds good. What other ones have they worked on?
Well, remember the Sagittarius A star picture we were all looking at earlier?
Yeah, of course.
Well, do you want to hear it?
What, we can hear that one too? Brilliant. So, Michael, I think it might be time for us to do a little recap on what we've learned about black holes on this episode. Cue music.
Number 1.
1. Black holes, regions of space where matter is so crushed and condensed that the gravity is huge and light can't escape.
Number 2.
2. Black holes are formed from stars collapsing onto themselves.
Number 3.
3. You can get supermassive black holes, which are just essentially like black holes, but like 20 or 30 billion times bigger.
Number 4.
4. Using telescopes, we can take pictures of them and translate those images into sound.
But there's something massive, something big we haven't covered yet, Michael. What happens if you fall inside a black hole?
Do you like spaghetti, Dan? You might not be able to look at it in the same way again.
Yes. Well, this is sort of one of the classic questions. And if you do pass the event horizon, it's quite interesting because the gravity is so strong. The term, Martin Rees used the term spaghettification. And that means that if you approach the black hole feet first and went past the event horizon, what happens is because the gravity is so strong, the strongest gravity would be felt by your feet, and so you actually sort of get extruded into something like a pool noodle as you fall into the black hole.
That does not sound good.
But believe it or not, Dan, the bigger the black hole is, the less your chance of spaghettification.
What happens is that the gravitational field outside the event horizon is not changing as fast. So this means that an astronaut could pass into the event horizon of a supermassive black hole, probably without being torn apart. But again, once you reach inside the event horizon of a black hole, you can't really communicate in other ways. So you can't phone home, or you can't even tell your friends outside that you are still alive and you are seeing the interior part of a black hole.
Right. Okay. So this isn't great news either. Let me get this straight. We'll either be spaghettified, turned into like a pool noodle, or if you do survive by some freak event, then you won't be able to tell anyone where you are or what you're seeing.
That's right.
Brilliant. That's like frying pan on the fire. So there's really no way of knowing then what's inside a black hole, I guess.
Not really, no, and that's one of the biggest mysteries.
There are many mathematical theories. The reality is that we will never be able to explore the interior part of a black hole, simply because if we get inside it, into a supermassive black hole, we will see something, but we will be completely unable to tell our experiences down on here on Earth.
Right, okay. Well, I think we've done very well at sorting out lots of mysteries of these amazing objects in space, but it sounds that Fabio's telling us that is one mystery that we may never be able to solve.
But that doesn't mean we can't come up with our own ideas. Perhaps our listeners would like to tell us what they think is inside a black hole. We'd love to hear your theories. Get in touch with us at hello@science-nature.co.uk.
Yes, but I've got one more question left. Just one more question. But it is a biggie. What's to stop black holes from swallowing up the entire universe, sucking everything towards them?
Yes, that sounds like a pretty terrifying thought. And also, if you're talking about supermassive black holes, but I think we can rely on this event horizon. Only a certain number of things sort of pass by the event horizon, and so those things that sort of go into the sort of sphere that is sort of beyond the event horizon, they fall into the black hole. But things can sort of naturally pass by, and as long as they don't get too close, they're fine. So a black hole isn't sort of actively sort of sucking everything in. It's only that things that sort of drift past and into its sphere of influence that get sucked in.
Oh, right. So it's not as if a black hole is like Pac-Man going around and gobbling everything up in its sights.
No, they're more like a whirlpool or a plug hole, as Ziri said earlier. You actually have to be close enough to them to get sucked in.
And Michael, just to be like a 100% clear here, I don't need to worry about Earth or my house and my cat getting eaten up by a black hole anytime soon.
No. In fact, according to Amelie, we could even be as close to a black hole as we are now to the sun and still be okay.
So if we imagine, for example, right this second, somebody were to replace our sun by a black hole of the same mass, we wouldn't feel anything on Earth. The Earth would keep going in its orbit, just like nothing happened. Well, of course, we would miss the sunlight, but otherwise it's not like we would be sucked into that black hole. A black hole would have to come really close to the Earth for something to happen.
Yeah, I definitely miss the sunlight, but that is very good to know.
Yes, I won't be having any nightmares about black holes tonight.
Well, on that positive note, we should probably get out of here before we get sucked in again by these huge mysteries of black holes.
Good idea. Now, don't forget, we'll be back in 2 weeks' time for our next episode, where we'll be walking with dinosaurs.
Yes, we'll be talking to the top dinosaur experts and finding out just how they know what dinosaurs looked like when they were alive. Is there anything you've ever wanted to know about dinosaurs? We'd love to hear your questions. And also, could you tell us, what is your favourite dinosaur?
Get in touch with an audio or video recording at hello@science-nature.co.uk. Until then, stay curious.
Thanks for listening to The Week Junior Show, which is made by the same people that make The Week Junior magazine. You can get a free trial of The Week Junior by heading to theweekjunior.co.uk/podcast and using the code podcast at checkout.